with the next speakers, we are leaving the finance sector and moving into another sector, the mobility sector. Dr. Fritz Schinkel, Head of Quantum Consulting Team at Fujitsu, and Stefan Wegele, Software Architect at Siemens Mobility, are here on stage. Here they are already. Let me shortly introduce you. Fritz Schinkel is leading a group of quantum consulting and programming experts transforming quantum technology into applicable solutions, and Stefan Wegele holds a doctorate on the topic of real-time optimization for dispatching in rail transport and works with Siemens since 2012 in the area of rail control systems. Their presentation wears the promising title of Combinatorial Optimization of Train Timetable, Fulfillment after incident, and is about a quantum-inspired approach to minimize delayed times caused by accidents on the railway. I think all our hopes are now on you, and the stage is yours. No pressure for your presentation, but welcome on stage.
Yep. Thanks for the main.
So, willst du von? Okay.
I will first show the objective from the customer point of view. So Siemens is building traffic planning systems, traffic control systems, and traffic management systems. And here we try to resolve a real-time, real-world examples for traffic management system. As a use case, we selected a network from a relatively small country, from Norway. Norway publishes the infrastructure data in microscopic quality on the internet, free for research purposes, and also the timetable. So it's a very nice example with exact infrastructure. And so also you see on the left side the map of the Norway. So you see it has long distance areas and on the limits of the country, and starway infrastructure in the middle around Oslo. And then if we go in the middle of the picture, we see the track infrastructure at the edges of the country. You see single track lines with a lot of crossing stations. And in the bottom you see the railway station for Oslo, having many lines coming together and sharing a lot of different tracks inside of a station. And if you look on the completely right side, you see the time distance diagram. So the upper part of the diagram represents train movements at the limits of the country. So you see very few trains per hour, but crossing around on a single track line. And as soon as they come into the Oslo, the traffic dense is increasing, so you have train headways about 2 minutes, so it's some kind of metro. So you have a mixed traffic with single track lines with crossings moving into Oslo and becoming a metro. So this is more or less a use case for commercial traffic management systems. Even bigger countries like Germany has a set of control centers, so it's separated into 7 control centers around this size. So this is more or less the objective. We want to optimize in case of disturbances.
Short interruption, we should go to stage for being in the recording.
Okay. Our objective was to have a proof of concept. And this huge network with about 5,000 kilometer tracks and about 2,000 trains movement per day is too big for proof of concept. So we decided to create partially simplified, but having still sufficient complexity network representing this entire topology. So we created a mix of double track lines and single track lines around 8 stations, and put there about 2,000 trains. So it's similar to what we have for Norway, the entire country. So on one hand, we reduce complexity of traffic management system. We use constant running times for the forecast. In reality, you have to take into account acceleration, deceleration, changing the speed profiles if you change the track inside station. And we avoided or neglected blocking stairs. So normally the train movements is blockwise. So you occupy one block and only one train is allowed to visit this block. And the next train can come into this block after this block is released by the previous one. So you have always one block between trains. So we estimated this behavior using headway. That means one train can follow the next train after some headway time passed. On the other hand, we increased complexity because the infrastructure is still limited, but we have about 2,000 trains inside, having more conflict potential between them. And we think the results of the proof of concept can be transported into the real application. And this is more or less the initial task given to Fujitsu to resolve with their method.
Okay, yeah. Should I move over there?
Yeah.
But you can stay. Okay, so we had understood this problem after a while, and I try now to show you first in one slide what we understood and how the concept is and what we think we could do different in the future to bring combinatorial optimization into the game. So as you've seen already, we often use here these time path diagrams. So we have here the path, 3 stations, A, B, C, and the lines between them. And downwards we have the time, and there's one train traveling from A to C, and the other from C to A. And everything is fine here. We see at station C, they come quite near, but they have different tracks and they can travel this way. That's a schedule, so that works. And this is, as Stefan said, typically managed in different management centers. So one human who looks for disturbance with his software only looks to a part of that and will optimize then in such a part. And what can happen there is, if we now have a delay, we can make different alternative solutions for that, and for which we decide that depends on the scope where we look at this. So if we have this situation, we have at B a certain delay, and now this should be handled. And in this simple example, we can imagine 2 different solutions. One is that the train traveling from A to C is brought into the target as fast as possible. We saw in the original one, first this train traveled from B to C, but now it is too late. The other train is already on the track. It's a one-way track, so it has to wait. And after it has passed that, now in station B, it can travel as fast as possible to regain some of the time. So that could be one possibility, and that's the natural one if you look from that perspective here of that person where the delay occurred. So that's what we should do here. But of course, if you look here, there could be the other way around. So we could say, let's travel the train as fast as possible. And oops, now we have a conflict. It would crash into the other train here. So that train now has to wait. And as you can see here, it has a bit more opportunity to regain the lost time. And yeah, it in the end is back on track when it's at station A. So if we now look from the reduced scope, perhaps you would say, yeah, here we have one local delay. Here we have 2 delays. It's complicated. We take scenario 1. But in the overall, we have at the end here still a delay in scenario 1, and in scenario 2, we are back to normal. So that's from that perspective. If then there are other areas aside, that's a better solution. Of course, we repair it, and in the other way, we don't know what happens in the next part. And so that is the idea, not to look to the best local solution and then stitch together something from that and try, and of course solve conflicts that stay, that needs to be done anyway, but to look for good local solutions and have different alternatives and combine them in a combinatorial optimization to a globally best solution. So that is like the algorithm looks like in complete beauty. So we get a schedule with a delay. So the delay makes typically conflicts. Here we had a very nice scenario where they matched in the next station, but normally even the first delay would produce conflicts, and then we have to produce alternatives. We're doing this in waves, so that means we have a certain set of delayed trains or trains with conflicts, and then we generate alternatives of specific type for all those. And they produce, of course, new conflicts, and that's then part of the next wave of generation, if that's necessary. And then we have a lot of possibilities, and there's then the quantum technology in the game. So to select now from this huge set of alternatives per train, several things, exactly one that is taken into the plan, and that of course should then be a very good in terms of a good schedule. And we can do this also in a loop, and as we saw from our experiments, it was very hard to avoid securely every conflict with it. So we definitely needed another classical algorithm in the end, this temporal progressive conflict resolution, which just looks for remaining conflicts and then solves them by, as we've seen in the example, by passing first one of the trains and then the other as fast as possible behind it. So that is the way we do it in course flow. Here's some details about the alternatives. That was also pretty new for us. How could we do this here? And we found 3 types of alternative methods to generate things, and with that then we could show some results. So the first one is what we call the regain wave. That's at the very beginning when we have delays typically. Then we could say this train could travel as planned with the same speed, so the lazy train, so to say. Or the other alternative would be drive as fast as it's allowed on the specific area, and all the other constraints from, of course, waiting in the stations, etc. And these were the first 2 alternatives. Then there's a typical thing that can be solved very easily. That's in stations. So when we have in stations a conflict that we have generated 2 trips that collide on a track, then we simply go to the parallel track. And a little bit more complicated is on single lines. When we have a conflict, then one has to wait for the other. And what we generated were 2 pairs of solutions. So first here the left one waits and does it in 2 ways, continues with the lazy method with its original speed and with a speed up, and the same thing from the other side. So that was what we call the delay wave. Of course, for the conflict we delayed the trains which are part of that conflict. Okay, and then we had to evaluate that. So we needed some kind of targets, and it's all together here in this optimization metric. So we have here on one point the number of conflicts with a certain weight. So you could nominate that as a cost for solving the conflict, not as a cost for accepting the conflict. So we never make crashes here. And the other is a mean over the delays in the stations where the train stops. And that is divided by the runtime of the train, so to have not an overweighting of short trains here with this metric. And we can balance that a little bit so that we can say we want to find less conflicts, or we want to find a better optimization in the delays. And then we did that with 2 setups. So this is the algorithm from the beginning, more or less. We did it a little bit different in the loop in these 2 scenarios. On the left-hand side, that was something where we only run once the rest conflict resolution after the loop. And so we could say to the algorithm, look a little bit also on the conflicts. So there was avoidance of conflicts, the primary target, and the delay was weighted a little bit less. So in that sense, a little bit longer journeys, but less conflicts, so less to do for the final resolution. And on the other side, we changed that and had the resolution every time in the loop. And in that way, we also had to reduce the conflict weight, because otherwise we would find the solution from the last round again, because that is a conflict-free. And that's what we not wanted to see. We wanted to have an improvement there. Yeah, and these 2 experiments here in 10 cases. So we have first the blue one, where randomly delays were injected to 25% of the trains. If we only make the deterministic algorithm with conflict resolution, then we get these blue results. Mean delay up to 1,000 seconds here. And the green one is the second algorithm. Most of the times it's better, but it's random. It can also happen. And I'm sure it could also happen with the third algorithm, but less probable. It can also sometimes be worse than the simple resolution, but in the vast majority, it's a great improvement. And yeah, the purple one is the algorithm where we have in each loop conflict resolution and do it then that way. So this was a first hint that this to bring additionally to the conflict resolution as it's done today, which is used here in a very primitive form, to be honest, but to see that bringing additional these alternatives and the selection of alternatives with a global view could bring a benefit. So that's what now, of course, needs to be hardened in ongoing tests and proof of concept. So here first is used as rapid prototyping a Python framework where we did this, and we are now looking into a more sophisticated solution. The network will become more realistic. We will have the current preparation algorithms from the software we have for alternative generation, so much better alternatives, so to say. And we also will test it with a C++ network to prove that the preparation time can be brought to a value less than a minute, so that it makes sense in the daily work. So it would not make any sense if we would use here an hour or something like that to repair the ongoing schedule. Okay, so it's just 0. Perhaps we have time for questions. No, I think it's.
No, we have time for applause, of course.
Yeah.
If there is a question, we have time for one short question. Yeah, I saw a hand.
Thank you very much for this very interesting talk. Just a brief question. Did you also look into quantum algorithms for that problem? So for example, if you have created that QUBO for the digital annealer, did you consider solving it on a quantum annealer or something like that?
No, we just solved it on our Fujitsu digital annealer here. It's the number of bits that we're using here were over 15,000, and so that's limiting the other technologies. That was a reason for that. And yeah, we are always in the situation that we have to compare with classical optimization technologies and not so much these hardware comparison. That's a good way to go with quantum annealing, but it's not our purpose to compare that in the first task.
Okay. Thank you very much for joining us here and for your presentation.